Hi, everybody. Thanks for joining today's session. I'm Derek Higgins. I'm Senior Director of our Enterprise Data Science team at Blue Cross Blue Shield of Illinois, Montana, New Mexico, Oklahoma, and Texas. I'm here with my colleague, Sonia Wexmonsky, who's a Senior Data Scientist with us. We'd like to talk with you a little bit today about some practices for storing artifacts that are associated with data science projects. So we've worked at a few different organizations around the data science space, some smaller organizations, some bigger organizations, and we've seen how teams tend to organize their projects in terms of the artifacts associated with them. Some good practices and a lot of practices that maybe are not a good idea to replicate. Before we go into that, though, let me tell you a little bit more about us as an organization. So we're Blue Cross Blue Shield of Illinois, Montana, New Mexico, Oklahoma, and Texas. So we're one of the Blues. These are health insurers who do business under the Blue Cross Blue Shield trademark. But we're a little bit unique among these Blues in a couple of ways. For one thing, we're a pretty big health insurance company. We're the fourth largest private insurer in the United States. We insure 1 in 12 American adults, but also because we are a not-for-profit insurer. So we are owned by our members. So we certainly have a financial incentive to control costs and ensure that we use our members' premiums wisely. But we also have good alignment with our members' interests otherwise, ensuring that they get good access to care and we support the communities in which they live. Okay. So the first type of pattern I want to talk a little bit about is one in which we see there's really not even one place where the whole project lives. There's really not even a central repository or starting point for looking at what constitutes a data science project. So some of you have probably had conversations that go a little bit like this, where you've got some team that you work with, maybe you do modeling, and this team works on data pipelines and provides inputs to you. And one day you just see that things have changed in some way that is surprising to you. So you reach out to the person on this team who's responsible for it and say, can you tell me a little bit about whether something has changed with this variable? It seems kind of different. And they'll say, well, we did make some changes. We're always making changes, but nothing that we think should really be of any consequence to you. Okay, but can you tell me exactly what happened, exactly what the changes were? And then maybe if you're lucky, you can get them to email you a copy of the code or a snapshot of the code as it exists today. Or maybe you've had a similar conversation on the other side where you have a team that is consuming the outputs of your model and they're showing them to the users in some way, but the display isn't exactly what you expect. So you reach out and say, can you tell me exactly how you are rolling these scores up to be shown in your dashboard? Well, it's the average. Okay, well, the average, but is it the average of all the scores on a day or average by members on a day? Not sure. Let me get back to you when I get the right answer to that. So these are both kind of frustrating conversations, right? Because there's some dependency between your project or your code and other teams, but you can't get immediate ground truth or you can't get transparency about how your code is operating with in this larger context. This will not be surprising to those of you who are familiar with Conway's Law. So Conway's Law says any organization that designs a system defined broadly will produce a design whose structure is a copy of the organization's communication structure. And in data science, often our teams look something like this, where there's a data science team that does some modeling, maybe some other things. There's an adjacent data team that develops data pipelines. There's a front-end team or an application team that takes the outputs of the models and embeds them in some user-facing application. And maybe there's an infrastructure team that supports all of these teams. And if you have 4 teams collaborating together on this project, you're going to end up with 4 different code bases. And this leads to all sorts of problems. As we've seen, we've got this inefficient way of communicating between teams. It's this manual interface where you've got to reach out by Slack or by email or whatever the tooling is that your company prefers. It's hard to reproduce results end to end that involve the pieces that were developed by different teams, and just in general, big challenges for governance and for quality assurance. So starting from this situation, we want to move away from it. We want to move to a situation where we have more transparency. We can understand what's going on in other parts of the organization, where there's some versioning of code, and we can state our dependencies in terms of the versions in other repositories that we depend on. And there's maximal interoperability between systems. But it's not easy to do that, especially in larger organizations. For one thing, different teams can have different tool chains. So if one team is working in Python and the front end team is working in JavaScript, it can be hard to sort of negotiate that, especially given that different teams may have different levels of technical sophistication. So it may not be easy, even if it's in principle possible. It may not be easy for some teams to just adopt a different language or adopt a different set of tools to do their job once they've already got a process in place. There may be teams that don't write code at all, that really just use GUIs or manual processes to produce their outputs. So that you can obviously make it very difficult to have their process codified in a place that's transparent. And of course, even if we can solve all of these technical issues, there are other reasons why it might be difficult for teams to converge around a more transparent solution. That some teams may not have incentives to actually move toward transparency. So if we are able to get alignment about trying to move toward this goal, different tactics could be applied in terms of how to implement it. We might decide, well, let's take the code of all of these different teams, put it in one place, put it in one shared repository, for example, a GitHub repository. But that can be difficult to do, especially in large matrix organizations that have a certain degree of siloing. One approach that's maybe a step short of that is to use looser coupling to, instead of having one common repository, have multiple repositories, one still associated with every team, but at least a versioning scheme that's in place for each of those teams so that they can then be linked. That may also not be possible in some organizations, but at least the bare minimum we can shoot for is to have the code live someplace where it can be discovered, some public, organization internal public place. And to have some documentation around where that code is and who the person is to contact in case of questions. Okay, another pattern I want to discuss is that in which instead of a repository per se, we use a folder on a drive someplace as the location where we store a project and all of its artifacts. So some of you out there are probably in managerial roles, as I am, and have received emails like this in the past. This is actually an email that I got in the recent past when an employee left our organization, and it basically says, "Hey, this person has left, and they had a bunch of stuff on their computer. Can you please look through this and decide what is important to keep and what can be thrown away?" And unfortunately, this is the way that data science projects are sometimes, too often, transition from one person to another. A person leaves or a person becomes occupied with a new project, and all of their stuff is in a folder someplace that is dumped on the new person so that they can get oriented. And it's natural that this should be the case because a file folder is a way that we've been storing project artifacts for time immemorial, certainly before the digital era started. This is a set of file folders organized hierarchically on my desk that I use to manage my household management project. It's got stuff about my condo board and stuff about medical issues in my family and stuff about home improvements. So it's a natural way to store project information. And it's very explicitly the inspiration for some of the mechanisms we have in place for storing information on the computer today. So this diagram is actually from a paper in 1958 by Barnard and Fine, describing a hierarchical file system that they had devised for the IRMA Mark I system, maybe depending on who you believe, the first hierarchical file system for computers. And you can see from the diagram, it was very explicitly modeled on paper file folders that we use to store information and to group information according to category. But when we take this analog metaphor and translate it into the digital world, we adopt a lot of the limitations of hierarchical file folders for project organization unnecessarily. In the digital world, we can do better, but we in adopting this strategy, we carry over some of these limitations unnecessarily. So for example, lack of versioning. File folders do not allow for versioning of files typically. And often, I'm sure some of you have seen projects that are organized like as shown in this screenshot, where you've got different versions of some script that somebody has written, and because the file system does not directly support versioning, the author has to try to sort of shoehorn some versioning in there by adding suffixes to file names, .version1, .back, .final, maybe adding the date to some files to do some sort of ad hoc versioning. And even if we do have a file system that supports some sort of versioning, for example, SharePoint or S3 buckets, often it doesn't track the stuff you really care about. Who made the changes? Why did they make those changes? A second problem, of course, is if you are using a folder on your disk to store everything associated with the project, with your code, your data, all the documentation, and so on, it lives and dies with your computer. If your laptop falls off your bike on your commute, if you have a catastrophic system failure, if you leave your laptop unattended someplace you should not, you can potentially lose all of your work, and it's gone. And the third problem with using file folders for storing project artifacts is it isn't good for collaboration. So if your project data lives on your machine, nobody's ever going to find out that it's there unless you tell them. And even if they do know to ask you for it, there's not much you can do just from a collaboration perspective. Maybe you can email them a copy of the code that they can work with, but then if they actually use it and improve it and adapt it to new contexts, there's not an easy way to get their contributions back into the work that you did. It's just an irreconcilable fork. So you may say, oh, these are all limitations of using a folder on my local drive to store data, but what about a shared drive? If we use the shared drive, maybe that would solve all of the problems. And it solves some of the problems, but I would say it actually makes some other problems even worse. So talking about risk of catastrophic failure, if your code is out there on a shared drive exposed to the whole company or exposed to everybody on your team, the more users that are working with it, the more opportunity there is for somebody to unintentionally delete something or to change something in ways that are not intended. And when you're talking about larger development teams, some of this versioning by convention, adding dates and so on, that's just going to break down. It's not going to work. Another, I guess, more minor issue is if you're using a shared drive for collaboration, you have to be connected to your VPN, to your organization's intranet all the time if you want to work with that code, which can be limiting. So when choosing some place to store artifacts associated with your repository, it should be versioned. The file store should be resilient, so you don't lose all your stuff. Should be transparent and allow people to find your code or find your project artifact and support collaboration within different teams. So you know what's versioned and transparent and supports collaboration? GitHub. So a lot of teams use GitHub as sort of a central portal for storing artifacts associated with their repositories, but you can definitely go overboard. And we've seen people go overboard. Once they learn about Git, they realize some of the benefits, and they tend to overuse it for things it really wasn't intended for. Just to give one example here, I'm sure you're all familiar with TensorFlow, large neural network library supported by Google. Recently, I cloned the TensorFlow repository onto my machine. If you do that, it's about 500 megabytes of data. It took me 10 minutes on my home network to do that. Understandable, because it is such a large project with so many branches and contributors. But there are other projects out there on GitHub, which are definitely not as complex as TensorFlow, don't have as many contributions from independent people, but are much larger. So I found one, names have been obscured here to protect the guilty, that is a relatively simple data science project, but because it contains a lot of image data, it's about 2 gigabytes inside. It takes me 40 minutes to clone this repository onto my local machine on my network. So in terms of what does belong in GitHub, we definitely want to put things in there that are code-like, tend to be small. They change a lot as people incrementally develop them. They're human readable. If you show differences between 2 versions of the file, they're going to be things that people can actually review and reason about and determine whether they make sense. So examples of that would be things like any kind of code, data pipelines, program code for modeling, configuration files that are text-based, the script that you write to set the hyperparameters for your modeling runs, documentation in an appropriate format, such as Markdown. Things that don't fit so well in GitHub would be things that are binary files, tend to be very big, don't change a lot over time. So examples there that clearly don't fit into a Git repository would be serialized models that are the outputs of our training scripts, the data that we train our machine learning models on, and then any sort of intermediate files that are generated in the course of running our data, whether it's transformed versions of our data or compiled executables. And there are always going to be a few kind of edge cases that we can argue about. I've had lots and lots of discussions about notebooks and whether notebooks really belong in GitHub or should be someplace else. They're kind of like code. You can to some extent get a meaningful diff of two versions of a notebook, but then they're also they also present some of the same challenges that we have with the things on the far right of this slide, where they can be large if they have embedded visualizations and images, and they can also potentially contain sensitive data in the output cells of the notebooks. So, we can continue to discuss those edge cases. So when we put things into GitHub that don't really belong there in terms of our data science projects, we run into a few types of problems. One, again, it's not good for collaboration. When it takes half an hour to clone a Git repository, that's really sand in the gears. For another thing, it can cause problems with production deployment, where if we have a bunch of stuff in our repository that shouldn't really be there, our repository is bloated, so that can lead to architecture problems, where if we want to, say, deploy that into an AWS Lambda, it may be too big for that. There may be sensitive data in our repository that isn't appropriate to put into a production environment. And then finally, there can be integration challenges where if we have some state saved inside the repository, like the state of a data set, that can become inconsistent with other parts of the pipeline that our system runs in. Again, we run into problems. So better to use GitHub for the things it really excels at. And there's no need to abuse it like this. In any case, there really are better solutions. Some better solutions in the Databricks platform. So specifically, Delta Lake is a great way to version data sets. You can store different versions of data and access them by timestamp. So identify the state of a data set at a given point in time. And then on the compiled model side, or serialized model side, there's the MLflow model registry that allows us to train, identify, and then deploy models from our machine learning code. And there are other solutions as well. So get large file storage. If we really want to use GitHub as our central entry point for data science projects, then we can link other types of data to that repository through get large file storage. And there are also solutions through cloud providers. So S3 and other blob storage services do support some sort of versioning for larger files. It might be a good complement to what's available in GitHub. Okay. So with that, I'm going to hand the baton off to my collaborator, Sonia.
So Derek just talked about ways to organize our data science projects and some of the pitfalls of not taking steps to do this organization in advance. Next, I'm going to talk about how we use our code and our repos to store an important output of our projects, which is the analytics decisions we make based on our data. So what do I mean by analytics decisions? As data scientists, we often write code that has hidden configurations and parameters embedded inside it. And this includes things like modeling parameters, filters we put on our population, thresholds, and decisions we make about how we're going to aggregate and return our data. Oftentimes, these parameters are not given to us by the business. Instead, they come from research that we've done on our own data, for example, observing an age distribution to set a threshold. And I think this is really what makes programming for data science different than general software engineering. As data scientists, we often start by exploring our data sets in an ad hoc way, and we make discoveries and conclusions. And then we take what we've learned to build code that goes into a reproducible pipeline for modeling and scoring. So this analysis, the analysis that we do can take many forms. It could include standard modeling steps like correlation analysis or reviewing variables for trends over time and fill rates. Or we may need to understand data models or learn stories about our data to understand our end users and their problems. So now I can say that I've spent many years working on projects and I've inherited code written by other teams in many different formats. And I've learned that it's necessary to treat this exploration as a first first-class work product. This means that it should be documented and memorialized for future readers, so that if we need to explain or debug these decisions that we've made about our configurations, then we have a starting point for our research. Sometimes I will go back to my own EDA that I've done myself 6 months earlier, and I review what I learned, and I'm able to save myself hours of work in understanding a particular problem that I've come across. So this is an example of a notebook that was written by a data scientist on one of my projects. Here he was doing correlation analysis, and he saved his work and his conclusions, and he wrote a clear description of what he did. And now I have a way to explain why we made the decisions we did on this project, why we dropped particular variables. And I also have a way to rerun what he did if our data set changes. So as Derek mentioned, there's different options for doing work in a shared environment. GitHub supports notebook rendering, so we can put these types of notebooks into GitHub, and this has the option also that it's pinned to our code directly. The Databricks environment also has a shared notebook workspace that has the advantage that teammates can look at each other's work even if they're working on different clusters. So now let's talk about the next phase in the data science lifecycle, which is building models and storing all the outputs and results of this modeling process. So this is also a step where it's really important to be cognizant of others who are going to be working on our projects in the future and who's going to be inheriting our work. So usually when we start modeling, we start working in a notebook. So this is an interactive environment. We can debug, we can review, and we can visualize the data that we're returning. But the downside, of course, of working in a notebook is that it's only local scope. Whenever we exit, whatever we've done is whatever model we built in memory is lost, and then all we really have left is the notebook output. So we were able to show that we've built a successful model, but when someone comes along and says, hey, can you apply that to this new data set? Can you apply it to the 2020 member population? We don't really have to do a way to do that. We have to kind of go back and start from the beginning. So then, okay, so how do we put our models into production? Well, so this is an example of one way to do it. And here we have a logistic regression equation that's been just pasted into our production SQL code, or the coefficients have been pasted into our code. And so this, I think that everyone who works in the insurance industry has had to do something like this at least once. And this actually is fine for a GLM. But as we move towards more machine learning methods, we do need a different approach. So specifically, we have things that we have to cache like hyperparameters. We have to serialize our models so they could be applied to future data. We're still also going to want to store things like test metrics, possibly store our training data sets, and other outputs that we may have. And by storing all of this, it allows another data scientist or another data science team to pick up where we left off, to take our work and continue the project when it's needed. So there are different ways to save these types of artifacts. MLflow, for example, has a Python API that can be called directly from the modeling scripts. But what is most important, whatever we're using, is that we take the time to think about what might be needed in the future for, to continue this project. Do we just need the bottom binary? Do we have to save our training data sets if they're difficult to recreate, or it can depend on when the data was created? It's also important to allow space for saving these details in the modeling process, to take the time to tag our code, or to use a model registry to call out when we've reached a checkpoint model that we want to save and share and possibly apply to other data sets in the future. So here's an example of grid search that was run with MLflow. And what you see is I have a way to kind of review all of our experiments, compare the hyperparameters and the model outputs. And the results are stored in a central location where it could be easily shared in a consistent format with other data scientists. So of course, model hyperparameters are not the only levers or knobs that we need to adjust in our project. When we apply a model, in production, we may need to adjust things like date ranges, or point to different file stores if we're moving from a development to a production environment. So we will have a lot of different parameters that we might need to adjust going forward. So there's a number of different tools and ways that we can do this type of customization. But generally what we kind of want to do is pull all these different parameters out and put them in a central location so it's easy to see what might need to be edited in the future. And so that we can do it without having to go back to our code repo and making code changes to support this. So one kind of straightforward and universally understood way to do this is with command line arguments. We can also use like YAML or JSON config files, and using config files allows us to have multiple concurrent configurations if we're possibly working on different machines. But whatever we do, it's just kind of important to think about what might happen. Of course, obviously, we can't anticipate everything that need to be changed. That's one of the realities of giving our models to an end user, that they're always going to come back with a new way of slicing the data that we hadn't thought of. But overall, this is kind of why we aim for having well-organized and transparent code and repos, so that these changes can be done fairly quickly. Just as an anecdote, recently at Blue Cross Blue Shield, we built a COVID-19 risk model. And this was something that the first version was done fairly quickly in about 3 weeks. And then after we deployed it, we decided to expand what we did to a larger member population. And the second model, one data scientist on our team was able to do that in about 3 days. And the reason that all that was possible is because that we had done our original work in a way that was well documented and modular and transparent. And she was able to take the pieces and put it together. So overall, that's kind of the goals that we have for this project. And this is kind of what we would like to convey, that our projects are well documented and they're transparent, and they put the work we do that's successful today and deployed today on a path where it's easy and well maintained and can be picked up by others in the future. Okay, so yeah, and thank you for listening to our talk. We hope that these ideas were helpful, and we're happy to take any questions at this point.